Welcome to the third and final video on the topic of density. In this video, we are introducing a concept called natural density, which is sort of like asking, what percentage of infinity do we have here? And that makes no mathematical sense, right? But here's what I mean. When we have a process that grows towards infinity, like, say, mapping the integers onto the unit circle in the complex plane, we can certainly measure what percentage of them map to a part of the circle up to some finite maximum value, right? And we can do that for any cap. As the limiting value, capital N, grows, if that percentage then stabilizes as it grows, we can take the limit. And that's what we're calling natural density. It's defined as the limit as n goes to infinity of the number of points in our chosen set S divided by n. Or it's the limit of the answer to our question, what percentage is in this part here? So here's like an imaginary example. As the maximum capital N grows, we count the number of points in our subset S, and that's a certain percentage in each row of n. And if that percentage then levels off and achieves some steady proportion of the whole, then we call the limit the natural density of S. Now, there's one part of the circle whose natural density is easy to know. Do you remember way back in video number 1, I showed you the Landau hypothesis? Well, this part here is equivalent to summing up a +1 for every point on the top half of the circle and a -1 for every point on the bottom half of the circle. And for the hypothesis, we want this to go to 0 over n to any power greater than 1/2, right? And you might remember that I mentioned that the smaller that value of epsilon is, the harder it is for this to be true. But actually, if epsilon was a full 1/2, so that we had the summatory Liouville function over n itself, it's a known result that the limit at that point is 0. That was proved by Landau. The more difficult statement that it converges near the square root of n is what Landau did not prove, but he showed that it was equivalent to the Riemann hypothesis. So with n in the denominator, we know that this expression is true. But think about it. If that's true, what is the natural density of the top half of the circle? Well, the summatory Liouville function is sort of like the difference between the top half and the bottom half, isn't it? And since the top half and the bottom halves together make up 100%, and the difference goes to 0, then each half must have a natural density of 1/2, right? 50% of the points are on the top, 50% are on the bottom. So that's a known result. Next, I'm going to define a term just for this video. It's not used in the paper, but I think it'll make the video flow a little better. I'm going to call any subset of the integers, or rather, any set of points that those integers map to under Wn, I'm going to call it balanced. If it has this property that within the subset, in the limit, as n goes to infinity, half of the integers map to the top half of the circle and half map to the bottom half of the circle. In other words, if the top half of our subset has a natural density equal to the bottom half of the subset. And by the way, I'll just give you a heads up right now. I plan to be real sloppy in the way I talk about these sets in this video. I'm going to be talking about them as if they are sets of integers, and you're just going to need to understand that I'm really talking about like sets of points on the unit circle after we apply the function w to those integers. But I'm not going to keep saying that. Like in my mind, it kind of is sets of integers, but each integer has a location on the circle that's determined by w. Something like that. Anyway. So we know the image of all the positive integers is a balanced set, the way I just defined balanced. But now we need to talk about subsets of those. For example, The prime numbers, 2, 3, 5, 7, and so on, we can find them on the circle. These are not a balanced set because they all map to the bottom half of the circle, don't they? None of the prime numbers have an even number of prime dividers, right? So obviously that's a set that's not balanced. What about the set of all even numbers? Here's the first 6 of them, 2, 4, 6, 8, 10, 12. Are they going to be balanced in the limit? Even numbers take the form 2n, and that n can be any integer, right? So one way to build them up is we could start with the set of all positive integers and multiply each one by 2. That's why we write it as 2 fancy n, right? That fancy n stands for the set of all what are called the natural numbers, which is just the positive integers. If we build our set of even numbers in that way, then we've started with a set that we already know is balanced, and we added one extra prime factor for each number. So then when we ask, like, what effect does this have on the number of prime factors, being even or odd, it's clear that they all switch sides. Omega, the count of prime numbers for n, has been incremented by 1. So odds become evens, and evens become odds. So the set of even numbers, which we're calling 2n, is balanced. And if you continue to think about that, you can use the same argument for the set of the multiples of any integer, x, like x and then 2x and 3x and 4x and so on. You're starting with a certain number of prime factors for each integer n. We call that omega of n. And then we're incrementing that by the same constant, omega of x. And for some values of x, that means you flip everything to the opposite side. And for other values of x, everything stays the same. But either way, you keep your balance. So we call the set of multiples of x xn, right, with our fancy n. And xn is balanced. So let's do a sidebar. Where are these sets of multiples located on the unit circle? Suppose we first locate our starting number x. It doesn't matter which number it is, just some integer x. Well, in order to locate this value, what do we have to do? X has certain prime factors that we put into psi, and we get its angle theta, right? And if we're looking at multiples of x, all of those same prime factors will remain present, plus some unknown collection of more prime factors. So the angle can't ever be less. It will have to be more. And that puts us somewhere in this area. Plus, in this area, since we'll have both odd and even numbers of factors. And by the way, I think xn is usually going to be dense in those areas for most values of x. What do you think? This is an interesting question. Can you come up with a value of x whose multiples are not dense in those two areas? Like between x and pi, and between the opposite of x and 2 pi. Maybe watch video 5 again and see if you can do it. I think I can build a number that has a hole somewhere so that it's not dense on those areas. See if you can do the same. Sorry, this isn't this isn't what this video is supposed to be about. But I thought of it while I was making the video, and it's a fun little exercise. But back to work, okay? I haven't yet told you what we want to prove about natural density in this video. So here it is. For some interval, for any interval on the unit circle, we would like to show that the natural density of that interval is equal to the natural density of its mirror image on the other side. Or in other words, if we take the union of two intervals that are exactly opposite each other, the resulting set has the property that we're calling balance. And we're going to begin the process of proving that using mathematical induction. I'm not going to explain what induction is in general, but if you're familiar with the concept, it'll make it easier to follow. And if not, I'll still explain enough that you should be able to follow the proof. You just might have to think a little bit harder about it. Okay, we know that xn, the set of multiples of some integer x, always has the property that it's balanced. The next step in our proof is to ask, what if we had two such sets? So we have xn union yn. Well, you might be tempted just to say, oh, of course, that's also balanced. But be careful. When we talk about balance, we're counting which points are in the top half and which points are in the bottom half of the circle. But there will be some points that are in both sets. So things are going to look like this. We're going to do a Venn diagram. All the points are either in the top half of the inner circle or the bottom half. So here we have multiples of x and multiples of y. And we want to count the points in the top half for both, for the union of those two sets. If we just count the points here and here, which we can do, we double counted the ones in the middle, right? The correct formula for the count would have to be like this. It would have to be this plus this minus that intersection point, right? The middle, since that was counted twice already. So it should be pretty clear that if the sets don't have any overlap, first of all, then you can just add their natural densities together and get the natural density of the union. But if they share some members, then you have to be more careful. You have to use this formula. And if we think it over, one way to show that the union of the two balanced sets is balanced would be to show that the intersection is itself balanced. Because if it is, then we don't upset the balance, so to speak, when we subtract that intersection to avoid double counting. But if it's not balanced, then the union of the two sets wouldn't be balanced either. But it turns out that it is balanced. If you just pick your two favorite numbers, x and y, and you start finding all the numbers that are in overlap, that are multiples of both x and y, you'll very quickly see what I mean. There's some least common multiple, right? You probably called that the LCM back in school. And then all the rest of the integers in the overlap are multiples of that, right? So just like xn and yn are defined as sets of multiples of an integer, their intersection is also a set of the multiples of an integer, and that integer happens to be the LCM. And since we know that all sets of multiples of integers are balanced, we can conclude that the intersection is also balanced, and therefore the union of xn and yn is itself a balanced set. So now we know that the union of any two sets of multiples is balanced. Next, we want to extend that to an arbitrary number of sets of multiples of integers. Okay, not just one and two, but many. And this is where we do some induction. Suppose as an assumption that you had already proven a result that the grand union of any n-1 sets of multiples of x1, x2, x3, and so on must be balanced. You have that proven, okay, up to a total of n-1. Now we add x sub n and all of its multiples to that union. So then is that balanced? Well, we have a union of two balanced sets here. So we need to just examine whether their intersection is balanced, right? What does the intersection of x sub n fancy n with that grand union look like? Well, it's not going to be a single set of multiples of an LCM like before. This is something a little bit more complex, right? What is it? Well, we can just build it up piece by piece. First, we list the intersects of x sub n fancy n with the sets of multiples of all the other x sub i's, right? And we know that that intersection on the first row is a balanced set of multiples of an LCM, and the second row is also, and so on. And how many of these are there? Well, n minus 1, of course, and each one individually is balanced because it's a single set of multiples of some number. So what do we have here? We have n minus 1 sets of multiples of some integer, and that's the thing that we just stated that we assumed. We assumed if you took the grand union of that many sets of multiples, the result would be balanced. Meaning, the intersection that we have to examine to see if our new result is balanced takes the exact form that we stated as an assumption to be balanced. So everything is fine. If you assume that all unions of n minus 1 sets of multiples are balanced, then you can conclude that all unions of n sets of multiples are balanced. And that's the inductive step. It's complete right there, right? So if you recall, we already actually proved what we want to prove for 2 sets. And now we have that 2 implies 3 and 3 implies 4 and so on. So that you can safely assume, or conclude rather, that any finite number of sets of multiples of integers, when you union them all together, is balanced. All right? Neato. And now we're going to use that knowledge to address intervals on the unit circle. First, let's look at a particular type of interval, starting from some arbitrary theta and going all the way to pi, right? Well, that plus its complement on the other side of the circle. We remember that if there's an n, some integer n that maps into this region, then all of the multiples of n also map into that region, right? Because they would have to be beyond whatever the theta value is for n. And therefore, we can describe this region as a union of an infinite number of sets of multiples, one for each integer that's in the region. And we can order them by size. Right, here we mean order them by the size of the integer, not by the size of the argument. We can order them from least to greatest and take the union of those sets up to some maximum n, and clearly that's going to be balanced. But we have to be careful about the jump from the finite to the infinite here, right? Does this also mean that the union of an infinite number of sets of multiples is also balanced? We have to think carefully about that. Remember that the definition of balance itself is about the natural density. And natural density is defined in terms of a limit as n goes to infinity. So we have an expression that's limited to some maximum n, and we can observe that this is actually equal to the infinite union right above it, except for some integers greater than the maximum x sub capital N, right? So when we're counting the number of members in the set S up to some maximum value of n, in our consideration of the natural density, we're always looking at a set of numbers that's contained in one of these finitely indexed unions, all of which we know are balanced. So as we learned, from the ghost of Leonhard Euler, measures at infinity are really just limits as n grows in an unbounded way. So yes, in the limit, this preliminary interval that goes from theta to pi is itself balanced. The final step in our demonstration is just to subtract one of these from another one, creating a new set that we know is also balanced. So if you're given A and B, then you just take the group from A to pi and then subtract the set from B to pi. And what are you left with? Finally, you have the balance property established for any arbitrary interval together with its complement on the other side of the circle. And that is what we wanted to prove. And this is a significant thing to know. We might not know what the natural density is on any given part of the circle or how much it varies, but we know that the natural density is symmetrical. And that will be critical because we want to show in the paper that essentially these points, W of n, all offset each other enough for the sum to converge. So if we have more points than average in some interval from A to B, it's like extra crowded or something, then we know that there's an offsetting, similarly crowded number of points in the interval exactly opposite that. And we're going to use that. So that concludes part 3 of our study of the various topics of density of Wn. And that means that we have reached an important milestone. The very next video will begin the central argument of the paper. This is the thing that everything else depends upon. We want to show that the sum of W of n converges for the square root of n. And that's not easy. But armed with the various facts that we have prepared so far, we will see if we can do it. I'll see you next time.